Welcome to all of our 12th standard SVM students. Today we are going to see solenoid and toroid, which is in our third chapter, magnetic effect of electric current. Here, according to our magnetic effect of electric current, if you supply a current flow in a conductor, around a conductor, magnetic field is produced. That concept based solenoid and toroid working. First of all, we are going to see about the construction of a solenoid. How we are going to construct a solenoid. We want to take an insulated copper wire. It should be a very long. That copper wire is going to wound in the shape of a cylinder. For that we need any one of that supporter, either magnetic material or non-magnetic material. Suppose I am going to take an cylindrical shape of that wood. This is a non-magnetic material. On that we are going to wound the copper wire. The copper wire is going to wound on that. So this supporter is going to take an invisible means the coil only we are going to take. Actually we need a supporter. Now in our book diagram, without supporter they are given. That's why I am going to draw the coil winding only. So we are wounding that wire on that supporter. We have a end A and end B. Through this coil we are going to pass a current. What we can be produced means magnetic field can be produced. So the shape may be helical shape or called as a helix. Helical shape. The solenoid is in a helical shape. That's why now we are going to define that solenoid. This is a form of coil. It's a long coil which is wound on that one of the supporter in the form of helix. So that's why we are going to define a solenoid is a long coil of wire in the form of helix. In the form of helix for a definition of that solenoid. But we have practically constructed that solenoid. Through that we are going to supply a current. Suppose the current may be flows from that A end to that B end. So how the current is flowing. Here ahead we are going to represent. So what we can say for the direction of the current flow means the current is flowing in this direction. That's why current through that coil is in a clockwise. Clockwise current. Here current flow is in a clockwise. Due to that clockwise current flow, in each and every turn, around each and every turn, the magnetic field is produced. So that's why the total magnetic field of that solenoid, how we can take and means, is a vector quantity. That's why the resultant magnetic field along that solenoid can be taken that vector sum of that individual turns magnetic field can say. So we have a direction of the magnetic field also. The direction of the magnetic field can be find based on that right hand pump rule. Direction of a magnetic field in a solenoid is given by right hand pump rule. We know already about that right hand pump rule. So, if the coil is going to place inside our right hand, then this holding finger says the direction of the current, then that extended thumb shows the direction of that magnetic field. So holding finger shows the direction of the current and extended thumb shows the direction of the magnetic field. So that's why the current is flowing like that. So inside that coil, magnetic field direction is this. As like that bar magnet, we have internal magnetic field as well as the external magnetic field. The internal magnetic field is acting from A end to that B end. So there we have a many number of magnetic lines, parallel lines of force inside that solenoid. But that lines are going to make a closed curve, extended in outwards. All lines makes extended in outwards. But as compared to the magnetic field in the inside the solenoid, the magnetic field outside the solenoid is negligible, very very small, because the very close lines are going to spread out in that larger region. The lines gaps are very large, so the magnetic field outside that solenoid is too small. So the total magnetic field internal and external is going to given in our another diagram. Same solenoid we are going to take on. Is a A end, is a B end. Current is flowing from A to B. The current flow is in a clockwise direction. Based on that, magnetic field inside that solenoid is this. According to that right hand pump rule, B end can be taken as a north and A end can be taken as a south. Another rule we have to represent that polarity of that solenoid. That rule is nothing but end rule. Based on that end rule, end A is south pole, end B is a north pole. Internally magnetic lines of force flowing like that. It is extended and outwards like that. But external lines are very larger distance. So that's why field strength outside that solenoid is negligible. But internally, there we are producing a uniform magnetic field along the axis. The total magnetic field inside the solenoid along the axis can be taken as the vector sum of that magnetic field produced by the individual tones. Suppose one tone produced magnetic field is B. Total magnetic field along the axis of the solenoid is taken as Bt is equal to. Suppose if we have n number of turns, that the total magnetic induction Bt is equal to n into B. So total magnetic induction along the axis of the solenoid is equal to number of turns into magnetic field produced around a single turn, or it can be says each turn, like that magnetic field is produces. Okay, around that solenoid, how the magnetic field is produced, direction of the magnetic field is given by right hand pump rule, and polarity of that magnetic field around that current carrying solenoid is given by that N rule. If a current flows through that solenoid in clockwise, nearer end becomes a south, opposite end becomes a north. Suppose if you are making a current flow in opposite direction, that is anti-clockwise direction, nearer end becomes a north, opposite end becomes a south. Like that we can say the polarity of the magnetic field for that solenoid. So after that we are going to calculate the magnetic field along that axis of that solenoid. For that we are going to use the Ampere Circuit Law. So we want to define that Ampere Circuit Law very clearly. This Ampere Circuit Law is going to apply to find the magnetic induction for that current carrying conductors. Magnetic induction for the current carrying conductors. But one thing we want to know, this Ampere Circuit Law should be applied for the symmetric condition only. In unsymmetric condition, we cannot apply the Ampere Circuit Law. It is the most important easiest tool to find that magnetic induction due to a current carrying conductor. But one thing must be required, in a symmetric nature only we can apply that Ampere Circuit Law. What is that Ampere Circuit Law? We have means is a line integral of magnetic field over a closed curve. Closed curve or loop is equal to mu naught times that mu naught should be taken, mu naught times of the net current in that closed curve. Or loop. So we can express that Ampere Circuit Law in an equation that closed curve. There is a line integral of magnetic field over a closed curve can be taken. Integral, that is a closed integral, can be taken as closed integral suffix, that is a C B vector dot dl vector equal to mu naught into I enclosed. This is the Ampere Circuit Law. So here B vector dot dl vector. How we can taken closed integral? Instead of that B vector dot dl vector, B dl cos theta equal to mu naught into I enclosed. This Ampere Circuit Law is going to use to determine the magnetic field along that long solenoid. Okay, for that long solenoid, how the magnetic field, the value of the magnetic field is going to determined by that Ampere Circuit Law. Okay. Next we are going to see that long solenoid. Which one may called as a long solenoid? The length of the solenoid should be very large as compared to the diameter. Then that solenoid is called as a long solenoid, and that solenoid is going to wound, that is a insulated copper wire is going to wound on that any one of that supporter, either non-magnetic material or magnetic material we want to taken. If you taken that wood, that is a non-magnetic material. On that non-magnetic material, we are wounding that coil very closely, that turns are wounded. That is called as a ideal solenoid. Solenoid which are the turns, which are having a turns very closely wounded, and their length is too large as compared to that either diameter or radius. That solenoid is called as a ideal solenoid. What is the difference between normal solenoid to that ideal solenoid means, for a normal solenoid, the turns are somewhat spreaded as like in our diagram. That's why we have a magnetic field inside as well as the outside. The outside magnetic field is very small, almost equal to 0. But in our infinite long solenoid, magnetic field is produced only inside that solenoid, not outside. Outside magnetic field is 0. That's why we are going to take on that very long, infinite long solenoid. Through that we are going to supply a current, and then we are producing a magnetic field along its axis. Okay. Next we are going to derive the expression for that magnetic induction due to a long current carrying solenoid. Magnetic field due to long current carrying solenoid derivation we are going to see. So the long solenoid where the length is too large as compared to the diameter and the turns are very closely wounded. Inside that solenoid we are going to determine the magnetic field by using a Ampere Circuit Law. So for that a total cylindrical shape solenoid is going to cut into two parts. One part is inside our plane of our board, that is half a part of that solenoid is inside our plane of that board, and the remaining may be outside. So for that we are going to take on a diagram as a infinite long solenoid in a cylindrical shape. So coil is wound like that. That's why current is passed through that coil in a clockwise means is upper view. Current is comes out. That's why dotted. Dot symbol for outward. For here current is in outward, and here current is inward. That is for cross symbol inward we are using. So if you take on like that, in our plane of the board current sheet is comes out, and upper current sheet comes out means lower one current is inwards. Due to that the magnetic field is acting this direction. Magnetic field direction. Along the axis we have a magnetic field. The value of the magnetic field along the axis of the solenoid going to calculate using a Ampere Circuit Law. For applying Ampere Circuit Law, there we want to draw a imaginary Amperean loop. That loop is going to take an part inner and a part outer. So that loop is going to take on in a rectangular shape. This is an Amperean loop, rectangular shape. The corner is going to the first A, B, C and D. The closed loop means started from A, then reach the A itself, and is lengthwise. This lengthwise of the Amperean loop can be taken any value, either small part or a total solenoid. Anyway, this solenoid has a total number of turns. Is going to take an N, diameter, D, current through the solenoid is I, and length may be taken is L. So N is the number of turns, I is the current through the each turn of that solenoid, length of the solenoid is L, then diameter can be taken as a D. Otherwise radius also we can be taken, that can be taken as a R. So for this long solenoid we are going to calculate the magnetic induction along that axis of the solenoid. So we are applying Ampere Circuit Law. What is that Ampere Circuit Law? Means line integral of that is closed line integral. Here the loop is started from A to that D we can take a total loop. That's why we are using the symbol C. Closed integral B vector dot dl vector equal to mu naught into I enclosed. What current is enclosed inside the Ampere loop, that may be called as a I enclosed. This is the total current in that Ampere loop we can take. So is the left side of our equation, is the right side of our equation. Now we are going to calculate this left side totally. So this is the closed integral B vector dot dl vector is going to split into 4 parts because that loop is in a rectangular shape. That's why we are partitioned into 4. Is from A to B, B vector dot dl vector plus integral B to C, B vector dot dl vector plus integral C to D, B vector dot dl vector plus integral D to A, B vector dot dl vector. So that the closed integral can be split into 4 parts. Is a 1, is a 2, 3 and 4. Here 1 is inside along the axis, but 2 and 4 is perpendicular to the axis, and the third one is outside that solenoid. So outside integral, according to our Ampere Circuit Law, outside we are not having a current. So that's why that integral value is 0. So that's why first we are going to calculate first one, integral A to B, B vector dot dl vector. Here integral A to B, B vector dot dl vector can be taken as B dl cos theta. Here theta is 0 degree. Here theta is 0 degree. We know that cos 0 degree is equal to 1. That's why integral A to B, B into dl alone. B is a constant that should be taken out. B into integral A to B dl. This dl value can be taken as any value up to its length. Suppose I am taken from that is 0 to L, then we can take BL alone. First integration value we are getting BL. Second and the fourth integrals so are having a theta value is 90 degree. Cos 90 is for second and the fourth. Theta value is equal to 90 degree. So cos 90 is cos 90 degree equal to 0. That's why that integral, that is a second and the fourth integral value becomes a 0. BL value is equal to 0. Then we have a third integral. That third integral is outside that solenoid. Outside the solenoid, there we are not having any current loop. That integration value becomes a 0. So that's why for a total closed integral B vector dot dl vector equal to BL alone. That is the product of magnetic induction along the axis of the solenoid and the length of the solenoid itself. Then from the Ampere Circuit Law, I enclosed value, that is I enclosed equal to I total. So what is the total current means? For each and every turn, the current through the each and every turn can be taken as I, and total number of turns are N. So that's why I enclosed equal to Ni. So that's why the right side value is Ni. That is instead of I enclosed, we are going to substitute Ni, and the left side is BL. So our Ampere Circuit Law, line integral force integral B vector dot dl vector is equal to mu naught into I enclosed. So we are going to substitute BL is equal to mu naught into Ni. We want to find the magnetic induction alone. That's why B is equal to mu naught Ni by L. That N by L, total turns divided by total length, can be taken as number of turns per unit length. That also can be represented as B is equal to mu naught small n I. This is the magnetic induction along the axis of current carrying long solenoid. That value is B is equal to mu naught Ni. Here, if that core is R core, their magnetic induction along the axis of the solenoid is B is equal to mu naught Ni. Suppose if you insert a soft iron, for what purpose we can insert a soft iron means to increase the strength of the magnetic field. There we have a soft iron means their relative permeability is very large. Their symbol is mu r. So if any magnetic metal medium is inserted inside along the axis of the solenoid, we can take in B is equal to mu r into mu naught Ni. Otherwise we can represent mu Ni is the magnetic induction along the solenoid which has the magnetic metal medium along the axis. So the general formula for R core is B is equal to mu naught Ni. But if it is a medium we have means B is equal to mu r mu naught Ni. Otherwise mu r into mu naught can be taken as a mu, that is B is equal to mu Ni. This is a formula for finding the magnetic induction along the axis of the solenoid. So that magnetic induction along the axis of the solenoid depends upon what are the factors means medium, number of turns, current through that each turn, as well as the length. If you take on this one, that is a medium directly proportional, relative permeability directly proportional, then number of turns directly proportional, current directly proportional, length inversely proportional, we can say. Otherwise, if you take on small n as the number of turns per unit length, B is directly proportional to mu naught, that is a medium, depends upon the medium. B is proportional to small n, proportional to I, we can take on. Okay, next we are going to see that magnetic field inside that toroid, how we can construct the toroid, as well as the magnetic field inside a solenoid, that is a toroid, can be determined based on that Ampere Circuit Law alone. Next we are going to see about that toroid. How we are going to construct a toroid means, already we know that infinite long solenoid. That infinite long solenoid or very long solenoid is going to bend into form in a ring shape. That end to end are connected to form a circular ring shape. That is called as a toroid. The toroid is a ring shape. Suppose the supporter of that toroid can be taken as one of that soft iron ring or any material medium we can take on. Then we are wounding the coil. Like that. This is the toroid. The solenoid is going to bend into join that end to end and form a ring shape that may be called as a toroid. If you supply a current through that solenoid, toroid, that inside that toroid produce a magnetic field. Want to check whether outside that we have a magnetic field also or not. So that's why we have taken point P here, point Q here, and point S here. Is a interior point. Is a exterior point. It is a inside toroid. So what about that interior magnetic field of our toroid we are going to find, but there we are using that Ampere circuit law itself. And what about that magnetic field in that exterior point as well as that inside the solenoid? Three cases we are going to tackle. There, case 1. That is, these 2 points are open space. Okay, there we are going to apply a Ampere circuit law itself. So that's why we are taken that outline diagram here. So total outline diagram. There that ring shape is going to taken this. Then we have a conductors, that ring upper. That is, current comes out means we use that dot itself. Then that current is going to inner. That purpose we are using that cross symbol. Inwards current can be taken as a cross symbol. Outward current can be taken as a dot symbol. So anyhow, this part totally in our diagram. We want to find that magnetic induction in the open space of that interior. It is the open space of the interior. So for that we are imagine that circular shape of that Amperian loop, and that loop may be having a radius R1. This point is already notated in our diagram P. So another one here, that is S. That is an Ampere loop 2. That radius can be taken as R2. Another outer loop going to taken. Their radius can be taken as R3. Is a loop 1 inner loop, that is a P point. And inside the solenoid finding, that is a loop 2. Outside there we are taken that loop 3. First we are going to find the magnetic field for that Ampere loop 1. Next we are going to calculate for Ampere loop 3, then loop 2 we are going to go. Further, here we are going to find that magnetic field in that open space of that interior of that toroid. So we are applying Ampere circuit law. Generally, Ampere circuit law is line integral closed integral B vector dot dl vector equal to mu naught into I enclosed in that Amperian loop. that enclosed part is P. There we know that no current in that Ampere in loop 1. So that's why this value becomes a 0. This value becomes 0 means right side fully 0. If in our equation right side is 0, left side also we can take on 0. So 0 magnetic induction at that interior open space. But even though there we have a perimeter of that circular Ampere loop, that perimeter can be taken as L is equal to 2 pi R1. But we no need this one because of no current in that open interior space. That's why I enclosed value is 0. So that's why the right side value total becomes a 0 means left side also 0. That's why no magnetic field in the interior open space. Next we are going to see that case 2. What we are going to find means magnetic field in the open space of exterior. Exterior point is Q. So that we can apply a formula. Line integral closed integral B vector dot dl vector equal to mu naught into I enclosed. For loop 1, no current is there. Now we are going to tackle that loop 3. For that loop 3 means a total toroid is inside that loop 3, Ampere in loop 3 means. Okay. There we have both current. What is that means? Inward current and outward current. Net current and is 0. What amount of current is acting inwards? The same amount of current is acting outwards. That's why I enclosed value is equal to 0. That's why mu naught into I enclosed equal to 0. So right side fully 0 means then for a loop 3 B vector dot dl vector equal to 0. Even though that the perimeter of that loop that can be taken as L is equal to 2 pi R3, but we have no magnetic field because of that net current becomes a 0. That is the case 2. This is case 3. We are going to see inside the toroid. Inside the toroid. Here we construct that Ampere loop 2. Where perimeter L is equal to 2 pi R2. Then total number of turns in the toroid can be taken as capital N. Total number of turns in the toroid can be taken as capital N, and there current through each turn is I. So that's why I enclosed equal to Ni. Then perimeter is 2 pi R2. So right side value is taken mu naught Ni. Left side can be taken as B into 2 pi R2. That's why B into 2 pi R2 is equal to mu naught Ni. So from that we can take B is equal to mu naught Ni by 2 pi R2. Then we can take B is equal to mu naught N by 2 pi R2 can be taken as a small n into I. That is the magnetic induction. Inside that is toroid, B is equal to mu naught Ni. So outside that toroid, we are not having a magnetic field. So for interior as well as the exterior, no magnetic field. Inside that toroid only we have a magnetic field. Same formula as like that solenoid, B is equal to mu naught Ni. But in our solenoid, small n, number of turns per unit length can be taken as, that is n by capital L only. For a toroid, n by 2 pi r, perimeter of that circle. That's all about that solenoid and toroid for determining the magnetic induction. That general formula can be taken as B is equal to mu naught small ni. Small n is the number of turns per unit length. Okay, thank you.